All right, so for today, we will continue our discussion regarding asymptotics. But in the last lecture, we only talk about the mathematical background. In particular, we talk about the limits, right? And also the small o, big O, same order, those relations. But these were all in the discussion of numbers, and we don't consider randomness in lecture 1. And even though in the end, we talk about the definition of the quantile function, which is the inverse of the CDF function. And the tricky thing here is that we need to consider the discontinuity points and non-increasing parts of the CDF function. So the inverse needs some consideration there. Okay, so for today, we're going to move on to the basic probabilities, and we will talk about modes of convergence. And just for your information, we have lecture notes from previous years, and I have already uploaded them to our Broom Learn website. This will be the reference for you if you want to do the note scribing for the new materials, or because this year, since we're going to add some new materials, we won't be able to cover every detail in the previous notes, but you can still use the previous notes for the other parts we did cover. So basically, the lecture note scribing for this year, for this class, will be more like a reassembly of old materials and new materials. And since we have a quite small class here, right, today we only have 3 people, I would say we can be quite flexible. It can be more like Q&A, and you can interrupt and ask questions whenever you feel needed. And of course, we have recorded the lectures online, so you can also review them. I'm not sure whether we have some students attending the class, but just not being here today. But I know one of the students told me that he will watch the lecture because he's away for a conference. But other than that, we'll start. So as you may know, that this class is about technical things, right? It's about the theoretical foundations. But I still hope that in the nowadays, maybe you would just use the results for your own research. So the most important thing is to understand what they mean and what they imply, and understand the intuitions, so that you will be able to have the big picture, and then you know when they might be useful for you. Okay, for modes of convergence, first question, why do we need them? The thing here, we'll talk about 4 modes of convergence. The reason we have 4 modes of convergence, but we don't have this concept for numbers, is just because of randomness. So now we're going to talk about this setting in which we have a random sequence. I'll just write on the notes so I don't have to repeat everything. Xn, and we have a random limit x. So these are all random. x1, x2, xn, and so on. They are random, and this x is random. And also, we may consider the general scenario where they are all d-dimensional random vectors, so not necessarily scalars. D could be greater than 1. Okay, so in this case, if we want to talk about this thing, xn, does it converge to x? If so, in what mode? So this question mark here indicates the mode. And we can think about convergence in many modes, 4 of them in total, and we will introduce each of them. So I know this is quite abstract, but to consider a concrete representation of a random vector or random variable, let's just say random variable for simplicity, that is d equals 1. How do we do it? My suggestion is to think about the realizations of a random variable. So in other words, if you think about realizations, then essentially we will have many sequences and many values of the limit. So if I say realizations, let me just write on top of it, then we can think about this as, I'll use lowercase xn1, I put it here, to xm capital B. So each of them is a realization of the random variable in the sequence, and we have capital B realizations. And for the limit, we can write x1 to xb. Then we can think about this convergence to happen for capital B times. So we can ask the question about, does my xn1 sequence, the realized sequence, converge to x1? Does my xn capital B converge to xb? So we can ask this for each of those convergence questions. So as you can imagine that here we're not just working with one sequence of numbers, but we're working with capital B sequence of numbers. And this B can be infinity, right? We can have infinite number of realizations for a random variable. Then we can have the four modes just as four ways to summarize these capital B converging or not sequences. So that's a starting point. Okay, and then the following discussion will be centered on this. Okay, so convergence, now for random sequences, we think about them in realizations for just to make it more concrete. So the first mode is the simplest one, and it's the one that we used in central limit theorem. This is called convergence in law. And we write xn converges to x, L means in law, but this can be written in another way. Xn converges to x in D, in distribution. Is this bright enough for you? No. Let me see. Maybe we can turn on the brightness of the TV. Yeah.
If I move it up too close, I can see it better, so it's on.
Yeah, let me see. Input. I'm changing this. All settings. Picture mode. Dark. Okay, this is better, right? Yeah, okay. Okay, we also write xn converges to D. Okay, and this means that essentially the definition is just for xn, the nth random variable in the sequence, its CDF function converges to the CDF function of the limiting random variable at any value x that fx, the limiting CDF is continuous. Okay, so basically, convergence in law or convergence in distribution is essentially the convergence of CDF functions to the limiting CDF function pointwise. We say pointwise that we talk about this convergence for every value x, but we are excluding the points, the values of x at which the limiting CDF fx is not continuous. We don't care about the discontinuity point, only for continuity points. And you can see that for this convergence of pointwise convergence of CDF functions, we didn't say the convergence has any mode because this is just a convergence of numbers. Okay, and this convergence in law, like I said, is always also called convergence in distribution or weak convergence. So when people say weak convergence, they mean this type of convergence. And yeah.
Does the sequence x, so the x1 to xb are a vector of random variable, correct?
Yes.
Do they have to share the same distribution?
No, not necessarily. No, not at all. But if you think about the realization I just introduced here, right? If you think, okay, we have capital B convergence sequences, then what does this convergence in law imply? It actually implies that at a given m, I summarize these capital B values into a CDF function. And also I summarize the capital B values in the limit into a CDF function. Then this CDF function, which depends on the index, the order m, it will become more and more like the CDF function of the limit. Okay, I'm just talking about distribution function to distribution function. So one thing to note here is that there could be no convergence at all in each sequence. That means maybe the first sequence doesn't converge, the second sequence doesn't converge, the capital B sequence doesn't converge. That could be possible, but the overall CDF function, which is a summary of those capital B values, that could converge. Okay, so that's why it's weak convergence, because it doesn't say anything about the values of xn and x. Their values could be totally unrelated, or they can be even independent, but their CDF function can be similar. All right, so this is one example. Let's look at it. So D is 1, scalar. So what does this mean? This means that for my xn, it's a scalar value, basically, because it takes value 1 over n with probability 1. So you can just say xn is equal to 1 over n. And your limit, x, is also a constant. Its value is 0. It has value 0 with probability 1. So we can verify that. So in this case, if you ignore their random variable notation, just think about the sequence, right? 1 over n, it will converge to 0. This is what we know. But now we think of them as random variables with probability 1 at this value 1 over n, and the limit has probability 1 to be at 0. Can we say that they satisfy the convergence in law? Then we go to the definition of convergence in CDF functions. We look at what is the CDF function of this xn. So, if the CDF function, if this is a probability mass at one value, essentially the CDF function is what? It is 0 before you reach this value 1 over n. Once you reach this value, it jumps to 1, right? So essentially here for xn, let's look at the CDF. So let me just put here, and it's 1 over n, okay? So this is x, and this is fxn at x. Okay, so let's mark two things, 0 and 1. So what happens is that the value stays at 0 until it reaches 1 over n, then it jumps to 1, and then it stays as 1. At this discontinuity point, we know at 1 over n, the value is not 0, but it's 1. So that's why we use the circle to mean that, okay, 0 is not taken at the value, but the solid dot here means that the value is 1 is taken. So this is the step function for the CDF. And for the same reason, the CDF function for x, which we write fx here, is also a step function, except that the change point here happens at 0. That's why we're using the indicator function to mean the step function. So this notation means that, okay, in the interval from 0, including 0 to positive infinity, the value takes 1. Otherwise, the value takes 0. So this is exactly reflecting the step function. Then we can see what? Okay, as n goes to infinity, what we see is that the discontinuity point, the change point of my CDF function of xn will go down and down to 0. So therefore, you see that, okay, let's compare the two. This is 1 over n, then there's 0. So let's jump up. This is the fx, okay? So we compare these two functions. Now we can see that for all the x values except 0, okay, every value except 0, their value of fxn, of the CDF function of xn, will change gradually to the value of fx, right? That's what we'll have. So the ones will stay as 1, but the zeros, which used to be 0 at a positive value, will gradually change to 1. So they will become like fx at that value, but except 0. The reason is 1 over n will approach 0, but never reach 0. So 1 over n will always stay positive. So therefore, 0 under fxn will always be 0 instead of 1. But under fx, 0 is 1. So therefore, 0 will not satisfy the pointwise convergence. However, this doesn't violate our definition of convergence in law, since 0 is the discontinuity point of the limiting CDF function. So it's not in our consideration. We can exclude it. And after excluding it, every other x value will satisfy the pointwise convergence. So that's why for this sequence, we can say it satisfies the convergence in law. Okay, that's the first one. First example. Another example, central limit theorem. So what this says, if you recall, is that if we have a sample of size n, we calculate the sample average, we denote that as xn bar, right? And we know that the sample mean will converge in law or in distribution to a normal distribution. That's what we know for central limit theorem. So I'm not going to be specific about the mean and the variance of the normal distribution, but basically this is a basic form. So in this case, what we are essentially saying is about the CDF function of xn bar. Okay, and here xn bar is a random variable because we consider our sample to be a random sample. So therefore, as we have a different realization of the sample, we will have a different realization of xn bar. And so we're saying that the CDF function of xn bar is converging to the CDF function of this normal distribution. That's it. That's the central limit theorem. Okay, so to summarize, convergence in law is only considering the distribution, overall distribution of a random variable in the sequence. And it doesn't really have any requirement about the values of xn and the values of x in one realization. In one realization, they could be very different. Second definition, now we have convergence in probability. That's why we write P on top of the convergence. So this is the most commonly used mode of convergence. So what does it imply? So you can see now we are actually calculating a difference between xn and x. Okay, if they're just both one-dimensional, this is just the difference absolute value. So what there's this saying is that we calculate the absolute difference between xn and x. We want this difference to be small. We want this difference to go down to 0 as n goes to infinity. That's what we want. But we know that xn minus x absolute value is random. It can take many, many realizations. So we are not being so strong to say, oh, every difference is going down to 0, or every realization is going down to 0. Because in this case, you can see that I will have, using my notation for the realizations, I would have xn1 minus x1 absolute value to xnb minus xb absolute value. I will have b such differences, and as I said, the capital B can be infinity, it can be many. So I'm not saying that everyone is going down to 0. I'm not requiring that. Essentially, I just require that this holds for the majority of them. Majority hold, and that's enough. So in other words, I'm saying this. So basically, for every epsilon is what we call the tolerance level, or it's like the neighborhood we're specifying between xn and x. So we know that for epsilon greater than 0, if we look at each realization and we compare that to this epsilon, we check whether this inequality holds. Because if it holds, it means that, oh, the difference is too big. It succeeds at my tolerance level. And I just look at across my realizations to see whether or I can call this violation, whether the proportion of violations is small. And I want this proportion to go down as n goes up. So in other words, if I increase my n, there will be fewer and fewer violations. That's what we mean. Okay, but there could still be violations. It's just that the violation proportion is going down as n goes up. Okay. All right, this is the convergence in probability. So that the reason why it is the most popular and relevant one for statistics is just because in statistics, we always care about high probability scenarios, right? We tend to ignore low probability, small probability scenarios. And this is the case. So we'll say in high probability, the difference between xn and x going down to 0. Okay, but in this case, you can see that we do care about the coupling between xn and x. They cannot be independent. Otherwise, their difference may be too big. And this is very different from convergence in law. So there's a counterexample. So you see that if I have xn following normal distribution with mean 1 over n, standard deviation 1, x follows standard normal distribution. So there are only differences in the mean, and they are independent. So in this case, it's clear that we have convergence in law because the CDF function of xm will converge to CDF function of x in pointwise, but we don't have convergence in probability. So if xn and x are independent, we will never have convergence in probability because their values are not going to be close. Okay, that's the second definition, convergence in probability. The third definition is called convergence in the Rth mean. Okay, and we write this R on top of the arrow of convergence. And it's actually about, when we say the Rth mean, we are saying, okay, it's the mean. By mean, we mean expectation. It's the expectation of the Rth power of xn minus x absolute difference. So it's basically absolute difference raised to the power r, and then we take expectation. And again, you see, once we take expectation, there's nothing random. It's just a fixed sequence, and then the convergence to 0 doesn't need to be specified in any mode, because for number convergence, there's only one mode. Okay, and the most useful one is when r equals 2. And this is called convergence in quadratic mean. So sometimes we write RQM for quadratic mean. And this is the most widely used thing for studying the mean squared error, right? Because if we have R equal 2, that's the squared error, and expectation means the mean. Okay, so if you think about our realization again, essentially what we are doing is that we calculate xn1 minus x1, first realization, absolute difference raised to the power r, and we have xnb minus xb raised to the power r. We have, again, b such r-powered differences, and the expectation is just their average, okay? And we're just saying that the average goes down to 0 as n goes up. Okay, so the major difference between the convergence in probability and convergence in the Rth mean is that for the convergence in probability, we care about the majority of realizations, while for the Rth mean, we care about the average of realizations. So I think this is also a very interesting question in applied statistics. That is, which one matters more in practice? In practice, maybe you only have one realization, right? Do you think the high probability result, as in the convergence in mean, matters more to you? If you think so, then your belief is, okay, I guess my realization is unlikely to be the minority. Then if the majority holds, then my realization holds. That's the rationale. But if you think the expectation one, the average one makes more sense, then you think, oh, maybe the average is more representative of my realization. But that is itself one kind of, how to say, world view, right? Because the average may not reflect you, well, maybe the high probability is a better guarantee. So I think that is something we need to convince or justify in our real use of statistics, because we only have one realization. That's just a thing. Okay, finally, we will have the last mode, fourth mode, almost surely. This is the strongest one. and we write xn converges as almost surely to x. So what this is saying is that every realization sequence converges. Okay, so essentially inside the probability, we're saying that, okay, xn has limit as x, and this event happens with probability 1. Almost sure convergence is also called convergence with probability 1. Okay, and it's the strongest convergence. Okay, so weak convergence in law, strong convergence almost surely. So what this means is what I'm showing on the top, right? So we actually have every sequence converges. So that means xn1 converges to x1 and xn capital B converges to xb. And this means no violation at all. And this is probably too ideal for statistics. So because we always have some exceptions with small probabilities. So that's why almost sure convergence is something mathematical, but I think for statistics, it's not so useful as the convergence in probability and convergence in the mean. Okay. Any questions regarding the four modes of convergence? And we will give you some examples to show, to demonstrate, or these are special cases to show why there are cases that one mode holds, but the other mode doesn't hold.
The first one.
Yeah.
For the first one, how does that involve the multiple realization?
For the first one, you mean the convergence in law?
Yeah.
Okay, basically, a distribution is a summary of the realizations, right? Yeah, you summarize the p-values into distribution. Yeah. But essentially, you see that it's weak because we are not considering individual sequence. We're just considering the overall. Yeah. Okay. Now let's continue. Look at some interesting counterexamples. The first one is that convergence in the rth mean or convergence in probability does not imply almost sure convergence. So what does this mean? It means that xn converges in the rth mean. This is what we wrote, right? To x doesn't imply convergence almost surely. And also, convergence in probability doesn't imply convergence almost surely. So the two things, we'll show you counterexamples. Why is that? Okay, so we can think about this construction. Okay, the construction here, it looks a little bit complicated, but it's actually simple if you write it out. So essentially, we are saying that z is just a random variable uniform between 0 and 1 for our, we will use it for our construction. Okay, and then our sequence will be as follows. x1 is a constant 1. x2 is a random variable depending on where z is. If z falls in the first half of the interval between 0 and 1, so we divide the interval to be 0 to 1/2. If z falls in, x2 is 1. And x3 covers the other half of the interval. So let's take a look at this. So essentially, I divide the interval 0 to 1 into 2 halves. Okay, so if z falls here, then x2 takes value 1. If z falls here, then x3 takes value 1. And then you can see their values are exclusive. So x2 plus x3 always equal to 1. Only one of them can be 1, the other be 0. And for the next ones, x4, x5, x6, x7. So essentially what I'm doing here is that I'm dividing the interval from 0 to 1 into 4 small intervals. So essentially x4, x5, x6, x7. So their sum is 1, and only one of them can take 1. The other 3 must be 0, depending on where z falls into. So I just continue doing this and I can generate my sequence, okay? So you can see the nearby adjacent xn's, they may have some dependency depending on whether they are in a group. So what this will happen is that you can see the sequence I create will never converge because somehow I will always have a value of 1 from time to time. So here, one of the 2 will be 1. Here, one of the 4 will be 1. And next, one of the 8 will be 1. One of the 16 will be 1. So in this construction, we will always have a 1 appear somewhere. So we would not have convergence almost surely because convergence almost surely require that my sequence converges, right? So my every realization will never converge because there will always be a 1 somewhere. But even though we have more and more zeros, but the 1 will still appear infrequently. But if we look at our definition, so we first understand there's no almost sure convergence. But if we look at our definition of the arith mean, then it actually converges because as your n increases, we will have fewer and fewer ones, right? So you can show that, and we're looking at the expectation. So if you have B realizations, then out of the B realizations, the chance that you will have a 1 will be smaller and smaller. So therefore, and you take this expectation, which accounts for the probability, then essentially you can show that expectation is going down to 0 as n goes to infinity. Right? Because it's about the probability, because the thing is our intervals are getting smaller and smaller. And when z falls in the interval, we get a value in our xn as 1. But that probability is very small, right? So we'll make the expectation small. That's why. And also, if you think about the convergence in probability, it also holds for this construction because you will have less and less likely to have violation. And violation is that xn and x difference is bigger than epsilon. And in this case, if you have xn taking 1 and x being 0, your limit is 0, then in this case, you are bigger than epsilon. You have violation, but that chance is also going down to 0. So that's why you see convergence in probability, convergence in the arith mean. They look at the collective behavior of your realization sequences, but almost sure convergence require convergence of every realization, and we don't have that. Okay, so this is an example to show this, to help you understand the concept. And another thing, let's move on, is that almost sure convergence also doesn't apply convergence in the arith mean. That is, if we have xn converges almost surely to x, it doesn't imply xn converges in the arith mean to x. Okay, why is that? Now we have every sequence converge, but we can also do a construction to introduce in every realization somewhere in the sequence to have an extremely large value. If that happens, when we look at just the realization convergence, then that value can be ignored, right? We just look at anything beyond that, later than that. But if we look at the expectation, then as long as you have in every realization somewhere a large value, then the expectation can stay large and it will not go down to 0. That's intuition. And this is the construction. So essentially, you see, in this construction, what we are looking at is still based on this uniform Z. We construct Sn to be in the interval 0 to 1. We look at between 0 and 1 over n. We assign the value here to be 2 to the power n, and the remaining to be 0. And you see, in this construction, the chance that xn takes a non-zero value is going down. It goes down as 1 over n because the interval is shrinking, right? The probability of taking this value is just the interval length, that's 1 over n. But once it takes a non-zero value, then the value is increasingly large, and it's 2 over n increases in exponential order. So in this case, you see that the decrease in probability cannot compensate the increase in value. So expectation is essentially 2 to the n, the value, raised to the power r over n, if we take the difference between this xn and the limit 0. So then you see this expectation is not convergent, it's exploding. And this is exactly the case I'm saying. In every realization, if you think about it, there will be a chance, even though the chance is getting smaller and smaller as n goes up, but there will be a chance 1 over n. It will take a extremely large value to the power n, and then that will make expectation not converge. Okay. So when this happens, right, almost sure convergence, but you don't have convergence in the arithmetic. It means that in the realization, the value you takes are not controlled. You may have some exploding values, even though that value occur only infrequently. Then after that, in the sequence, you have convergence. Okay, so because of this intuition, right, we know the convergence in the arithmetic requires some control of the values, of the realization values x and n can take. Then we have special cases where you can use almost sure convergence to imply convergence in the mean. Okay, so we will look at the two important results. So the first one is called monotone convergence theorem. Some people write MCT for that. So in this case, you put a constraint on your sequence. That is, your sequence is monotone increasing. So every xn is bounded by the following ones, upper bounded by the following ones. So x1 less equal than x2, less or equal than x3, and so on. And we then have the convergence almost surely. So this bounded thing also happens almost surely. That means in every realization sequence, you have monotone increasing sequence. So in this case, you can imagine that this exploding scenario will be avoided because the value cannot be all of a sudden high and then go down. If that's the case, if you have explosion, then you wouldn't have the convergence almost surely. So the two things tied together. This guarantees the convergence in every realization. This guarantees that in every realization, the sequence increases monotone. So there could be no up and down thing. So in this case, you can say, okay, expectation of your sequence, expectation of xn converges to expectation of x. So this is, you can consider this monotone increase as a regularization. Okay, so because we have to cover this basic thing in one lecture, I will skip the proof, even though the proof is there. And for this proof, we will use some of the facts to, I would say we will use some important construction from actually measure theory. And this is a technique from measure theory to help us prove this result, like how we from almost sure convergence to this expectation. And one thing to also note here is expectation. If we think about the general sense of measure theory, not just probability, because probability is a special case of that, expectation is essentially integral. We're integrating a function. And here we're integrating the probability density function, right? Essentially, that's how we get the expectation. It's the density function times the value, we do the integration. All right, so monotone convergence theorem, and also we have another special case where almost sure convergence implies convergence expectation. That's called Lebesgue-dominated convergence theorem. This is sometimes called a DCT. So now the constraint is not the monotone increase, but this dominance. Okay, essentially, we need the sequence xn absolute value be upper bounded by some random variable y, and the random variable y itself has expectation being finite. So essentially, you see that the issue we encountered in the counterexample, that is the explosion of the expected value. That's because we have some very large value, even at small probability. Then this expectation of y being finite guarantees that this won't happen. Okay, we won't have those exploding values. Therefore, the xn values will be kind of constrained. And because of that, then almost sure convergence can guarantee expectation. convergence. And these are the two major results. And just for information, in the proof of the dominated convergence theorem, we can use a lemma called the Fatou's lemma, which is also something regarding or just to give us some result about expectation of xn and expectation x, their relationship if we have almost sure convergence. But this is about some lower bound on the sequence. But dominated convergence theorem is about the bound on the absolute value. Okay, so to summarize, we talk about monotone convergence theorem and dominated convergence theorem. Both are ways to regularize the values that our random variable sequence can take. Okay. And another thing good to know is this alternative definition of almost sure convergence, which is good to know because it's written in a different form and in a form similar to what we have in the convergence improbability. So essentially, this is it. For every epsilon greater than 0, we have this going to 1 as n goes to infinity. Let's compare this to just convergence improbability and see what their differences are. So let's say that versus if we just have convergence improbability. This is for every epsilon greater than 0, we have the probability of xn minus x less or equal than epsilon converges to 1 as n goes to infinity. This is it. So if you compare these two definitions, what's the difference? So the difference happens inside the probability. So for the convergence improbability, we're only looking at the difference between xn and x and check whether that's under epsilon. While for this convergence almost surely, we are not just looking at xn, but everything after xn. So we're looking at all the differences, xn minus x, xn plus 1 minus x, and everything beyond. So we want all these differences to be under epsilon. So that's a stronger requirement, right? And actually, you can easily see this will tell us if we have almost sure convergence, then we must have convergence improbability. That's weaker. Okay, so essentially, you see this guarantee for all k greater than n. So essentially, it's saying that when I look at my realization, I'm not just looking at the nth value, and we look at xn minus x absolute difference, but we also look at everything after that. So they have to be all small. So this itself implies some convergence in that realization because everything stays small. Okay, we cannot have all of a sudden violation after n. But for this one, it's okay. So it's possible that every sequence doesn't converge, but you just have the overall violation going down. Okay, so that's the key difference. And this is the proof. I think the proof itself is interesting to read if you are interested, because basically it shows how we can rewrite using the definition of a limit. And this is the definition of almost sure convergence. The event that the limit of xn is x, we can re-express this using the epsilon language. That is, for every epsilon greater than 0, there is an n such that this neighborhood thing happens for all k greater or equal than n. So we're using this to do the alternative definition. Okay, so then the next thing is that we will tell you among the 4 modes of convergence, what can be implied from one mode to the other. And this is the very important relationships. Okay, first of all, almost sure convergence implies convergence improbability. That's the first thing. And this can already be seen from this alternative definition I just said. Second, convergence in the rth mean for some r, it doesn't have to be the square, it can be some r, other r positive implies convergence in probability. That's the second thing. Okay, and this can be shown by the Chebyshev's inequality, which we'll quickly show, because this is a very, very important result. So that's why we want to show you this proof. Okay, this is the proof for the second result. So how do we do it? This is a commonly used technique. That is, for the rth mean convergence, we look at expectation of xn minus x raised to the power r. And this can actually be upper bounded by multiplying an indicator function inside expectation. So essentially in the expectation, we have this rth power difference multiplied by the indicator function that xn minus x difference is greater than epsilon. Because this indicator function can only take two values, 1 or 0, then multiplying it won't increase our value, right? But this is a technique we can commonly use because if you know this indicator function, so basically this is inside expectation, the value is only 1. The value is only non-zero when the indicator value is non-zero. And when the indicator value is non-zero, it means that the difference must be at least epsilon. Then we can basically further find a lower bound for this rth power difference by saying it must be greater or equal than epsilon raised to the power r. Then we can move it outside of expectation because it's not random anymore. Then the expectation of the indicator function is just the probability. It's just the probability function, right? And then we know that this is actually, sorry, this is a typo. It should be greater or equal than, yeah. An expectation of indicator function is just the probability of that event in the indicator function. And this is what we call Chebyshev inequality. So basically, we can always connect the probability of violation to the expectation of the rth power difference. So essentially, you see that if we have this relationship, and if we know the convergence in the rth mean means the left-hand side go down to 0, then this probability also go down to 0, right? That's it. This is what we have for the proof why rth mean convergence in the rth mean implies convergence in probability. Okay, that's the second relationship. Now, the third relationship is this. Convergence in probability implies convergence in law. Okay, why is that? So we know convergence in law is the weakest one, right? And convergence in probability is stronger because it requires that the realization values of xn and x must be close. So for this one, this proof is also quite interesting because we basically make use of the definition of the CDF function. That's what we need for convergence in law. So essentially, we look at this event, x limit. This is the limiting random variable less or equal than any x0 value, and this thing. So essentially, what we're trying to do is that we are trying to use xn minus xn greater than epsilon, the violation, or we try to tie fx and xn to be close to each other because this violation happens infrequently. We try to tie them together using what we already have in convergence and probability. Then we can basically translate the probability that x is under this upper bound to the probability that xn is under this upper bound, and which is corresponding to the CDF function definition. Because essentially, this is what we have. So fx at xn at xn, this is essentially the probability that xn is less or equal than x0, right? So that's what we're translating into the probability event. And this is actually probability xn is less or equal than x0 plus epsilon. So we have that. And we can just decompose this probability upper bounded by this probability and the violation probability. And we do the same thing for this x0 minus epsilon. So in both sides, on both sides, we're just trying to use the epsilon neighborhood to make sure that x0 and x are close to each other. So then their CDF function can be close to each other. That's the general idea. Okay, so that's the three relationships. Again, if we order the four modes of convergence in terms of the strength in the following ways, we actually have convergence in law as the weakest one, which is followed by convergence in probability. And finally, the convergence in Rth mean and convergence almost surely, they are the strongest two. So they don't imply each other, but they both imply convergence in probability, and the convergence in probability implies convergence in law. That's the relationship. Okay. All right, so now, and except the arrows I just drew, other things don't hold. Okay, for all the other things, we have counterexamples. But there are some partial things we can say as exceptions. So these are what we call partial converses. First one is that if your limit is a constant c instead of a random variable x, this is the difference. The limit is a constant c. If that's the case, then convergence in law does imply convergence in probability. Because basically for the limit, your CDF function is just that step function, right? With a change point at c. That's it. So with a constant limit, then just the thing is much simpler because you don't need to worry about the limiting random variable to vary. It just takes one value, c. It's staying there. Okay, and the second result is related to what we just said about the dominated convergence theorem. It's basically an application of that. So we know that almost sure convergence doesn't imply convergence in the Rth mean. And the counterexample we just gave you is saying that if you have some exploding values that happen infrequently, Rth mean doesn't converge, but you can still have every realization sequence converge. So this upper bound on the Rth power of epsilon value is to avoid that exploding value. Okay, so this z upper bound must have finite expectation. And this is what we apply the dominant convergence theorem. So in this case, almost sure convergence can imply convergence in the Rth mean. And this Sheffield thing is similar, except that here we are just adding some lower bound on the sequence to be non-negative. And also we have convergence in expectation. And then we have convergence in the Rth mean. So this is also kind of like the regularization to avoid exploding values. Finally, this is good to know. If you have convergence in probability, then even if you don't have almost sure convergence, because you may have non-convergent sequence in every realization, but you must have a subsequence that converges in every realization. So this is another useful result for just translating convergence in probability into a subset, a subsequence, I should say, subsequence with convergence almost surely. Then it's just for technical convenience, because for almost sure convergence, we can treat it as just the real number or just as the non-random number constant convergence, because it's just convergence. We can treat almost sure convergence as just number convergence, and then we can apply any properties we have for that convergence. For example, we can apply a function, a smooth function transformation to the sequence and to the limit. If you have almost sure convergence, then you also have that. And then we can just apply that property. So these partial converses are not as important as the relation we show here because these are special cases. But I think they are sometimes useful, especially the subsequence thing, or they can help you understand, okay, why we have some exceptions or why the converses don't hold in general. We need to add conditions to make them hold. Okay. All right. Any other questions? We just quickly went over the four modes of convergence and we talk about monotone convergence theorem, dominated convergence theorem, which are for getting more out of almost sure convergence. That's it. Okay, for the remaining time of today's lecture, what I hope to show is, let me see. Yeah. I think I'm trying to cover the essence and the most important things we need to know. Okay. This is very important. I'm going to talk about convergence in law, just briefly to get us involved. So this is something we will not go through the detailed proof, but I think it's good to know. Helly-Bray theorem is regarding convergence in law. So what it says is that the following four statements are equivalent. So the first one is your convergence in law. And second one is that you can just translate convergence law to convergence in expectation of some well-behaving function, G. But this is saying that if you have convergence in law, then you actually have, let's look at statement G, hold for all bounded and measurable functions G, such that your limiting random variable x is in the continuity set of G with probability 1. So this is the most general way to say it. And B and C are special cases of G, and they are there just for the convenience of proof. So essentially, we ultimately want to say A and D are equivalent, and B and C are just intermediates. But B is saying for all continuous functions G. C is saying for all continuous and bounded functions G. All continuous functions G that vanishes out of the compact set, and so it only has a support in the compact set. And C is for all continuous bounded functions G. So essentially, Helly-Bray theorem says that if you want to prove convergence in law, you can prove either B or C or D, and then you will get convergence in law. But the three statements B, C, D are for all such functions, not just a specific function, a special case. That's for your information. But the reason why we need Helly-Bray theorem is because we can use Helly-Bray to prove this very important result. This is called continuity theorem. Some people call Levy's continuity theorem. So what is it about? So basically, on the right-hand side, it is so-called the characteristic function of a random variable. So this psi x n t is the characteristic function of xn at value t. And psi x is the characteristic function of x. So this says that if we can prove pointwise convergence of the characteristic function, it implies convergence in law. And this Levy's continuity theorem serves as the background for proving central limit theorem. That's it, yeah. So we are going from most fundamental to most specific thing. Because central limit theorem, to prove it, one way is to show that the characteristic function of your sample mean is convergent to the characteristic function of a normal distribution. Okay, yeah, that's it. But Helly-Bray, if you know Helly-Bray, then this will directly imply, yeah. Okay, so for the remaining time, I'll quickly say one thing about the use of okay, we'll talk about law of large numbers in our next lecture, so I'll hold that for now. But for today, I will say this is something I want to mention. Slutsky theorem and continuous mapping theorem These two things are very useful techniques in our research. First, Slutsky theorem is essentially saying that, okay, you can combine your convergence in two convergence sequences into one. Basically, you can use their combination to derive some results. So in this case, I'm saying if you have xn, I'm just using another way to write it. Xn converges in distribution to x. Okay, we write the D notation, not the L notation. Yn converges in probability to a constant C. But you know, based on what we just said, this can be implied by Yn converges in distribution or in law to C, because C is a constant limit, right? If we have both, then first of all, their sum will converge in distribution to their respective limits sum. And their product will also converge in distribution to the limits product. And finally, their ratio will converge in distribution to their ratio, to the limits ratio. That's it. So essentially, we can combine two sequences into one. And this is convenient in deriving the asymptotic distribution of our test statistic. So convergence in law is most useful for deriving asymptotic distributions, because then we can use that for many things, right? Like if we want to get a confidence interval for a parameter based on a statistic, then we rely on the statistics asymptotic distribution. Or if we want to convert the statistic into a p-value, then we may use the null distribution under asymptotics. Okay, so asymptotic just give us closed form to work on. Yeah, and also I can tell you that all these things can be changed to convergence in probability, and that will still hold. Okay, all three statements. And continuous mapping theorem. So this is also about transforming one convergence sequence in distribution to another sequence by a function map G. So here G needs to be a function continuous at all points where X has positive probability. Okay, so basically where X, the limit, can possibly take values from. And then you can apply this G to your convergence sequence, and then G of Xn will converge in distribution to G of X. This is also very useful, yeah, for deriving asymptotic distributions of a statistic. Okay, so that's pretty much it. So today we basically give you the foundations from probability about the convergence of random variable sequence. And the application of that is for deriving properties of our estimator in statistics. Because in our statistic, the estimator is a random variable, and in our context, n is the sample size. Basically, if we have a larger n, then our statistic behavior will change, right? So then convergence in probability is mostly useful if we want to use our estimator to estimate a parameter. We want the estimator to be close to our parameter in high probability, right? And also closer and closer as n goes up. That's what we want. This is something called consistency. We will talk about that next time. And also for the distribution of our statistic, we also hope to have some well-behaving asymptotic distribution. And the foundation of that is the central limit theorem. And that can be the basis. And we can apply Slutsky theorem, continuous mapping theorem. And also later we can talk about the delta method, which are all techniques for us to derive asymptotic distribution of statistics. Okay. All right. So then any questions before we wrap up for today? No. Then for our next Monday lecture, as I briefly mentioned in the first lecture, so I need to combine Monday and Wednesday lectures into one class. So on next Monday, we will have the lecture on Zoom because I won't be here, but we'll have on Monday. And I will record both lectures. So if you need to miss part of it, you can watch the recording. Okay. All right, so I'll see you next week.